In this lesson, we will discuss inductance. It is not all-inclusive of everything we need to know on the topic. Additional information can be found in the General Aviation Maintenance Technician Handbook and in Acceptable Methods, Techniques, and Practices of Aircraft Inspection and Repair. When previously discussing alternating current, we learned that alternating current is generated by crossing magnetic lines of flux with a conductor. This works whether we move the conductor across the lines of flux or the lines of flux move relative to the conductor. Through a conducting wire carrying alternating current, remember that the voltage and current are constantly increasing to a peak value and back to zero, while also changing polarity and direction every half cycle. This creates a magnetic field around the conducting wire that is continuously expanding and contracting and reversing direction. This changing magnetic field is moving relative to the conducting wire, inducing a back voltage into the conductor. If there is a second conductor in close proximity to a wire carrying alternating current, a current traveling the opposite direction will be induced into the second wire, which also creates a magnetic field. When the changing lines of flux from one conductor cut across a second conductor and induce a voltage into the second conductor, it is called mutual inductance. An inductor can store energy in its magnetic field, and an inductor tends to resist any change in the amount of current flowing through it. In a circuit diagram, the symbol for an inductor is shown below. This is a circuit diagram representation of mutually inducting inductors. The two vertical lines between the inductors indicate a solid core that the wires of the inductor are wrapped around. Nm shows the ratio between the number of windings of the left inductor to the windings of the right inductor. The inductance depends upon several factors: the number of turns in the coil, the spacing between the turns, the number of layers of windings, the ratio of the diameter of the coil to its length, the cross-sectional area of the coil, and the material in the center of the coil. A core of magnetic material greatly increases the inductance of the coil. Here we have illustrated several of the factors affecting inductance. A Henry, symbolized by the letter L, is the unit of inductance. Inductors in a circuit are added just like resistors are, whether they be in series or parallel. And inductors can be placed in a circuit just like resistors are. Inductive reactance is the opposition to flow of alternating current caused by the generation of a back voltage. It is measured in ohms. Unlike resistance, inductive reactance generates no heat and dissipates no power. When there are only resistors in a circuit, the Ohm's law is expressed as current equals voltage divided by resistance. When there is inductance in an alternating current circuit, the relationship between current and voltage can be expressed current equals voltage divided by inductive reactance. The formula for finding inductive reactance is inductive reactance equals 2 times pi times the frequency times the inductance. Here are a couple of questions to ponder. What happens to the inductive reactance as the frequency increases? What is the inductive reactance in a DC circuit? Let's find the inductive reactance in this example, where we are given an inductance of 44 millihenries, or 44 1,000ths of a henry, and a frequency of 99 Hertz. Remember, the formula for inductive reactance is inductive reactance equals 2 times pi times the frequency times the inductance. In this example, we have 2 times pi times 99 Hertz times 44 millihenries. When we multiply these together, we find out that the inductive reactance is 27.3 ohms. Inductors are used to filter out unwanted radio frequencies and to change the values of alternating current and voltage. Transformers utilize mutual inductance to change the values of voltage and current. Transformers are made of two coils of conducting wire wound around a common core, but not connected electrically. Alternating current flows into the transformer via the primary coil and flows out of the transformer via the secondary coil. The primary coil induces a voltage into the secondary coil. The relationship between the voltage in the primary coil and that in the secondary coil is determined by the turns ratio. The turns ratio is the ratio between the number of turns in the primary coil to the number of turns in the secondary coil. If there are twice as many turns in the secondary coil as in the primary coil, then the secondary coil will have twice the voltage of the primary coil. Since the product of the voltage and the current must be equal in both coils, then the current in the secondary coil must be decreased in inverse proportion to its increase in voltage. Transformers are subject to several types of power loss. Leakage flux results from not all of the lines of force set up in the primary coil cutting across the turns in the secondary coil. Efficiency is improved by utilizing an iron core. Copper loss resulting from resistance in the turns of copper coil. Iron loss, of which there are two types: hysteresis, the electrical energy required to magnetize the transformer core, and eddy current results from currents being induced into the transformer core, reduced by insulating the core.